some point I got to remember to empty these things off my hard drive or my laptop is going to collapse. Oh, there's nothing on the screen. That's a problem. It says HDMI PC2. So that. See, the trick is if you hit the button that says hide image, it actually displays on the screen because reasons. Okay, well, it's nice to see everybody. Welcome back to 68410 for another lecture today. I think today we might actually end on time. This is one of our shorter topics, but I always say that, and then we rarely do. So we'll see. In terms of announcements, logistics, all that good stuff, remember that we pushed back your homework deadline, I think, until Friday. Is that right? Thea, did we remember to put that on Piazza? Oh, fantastic. Good. So then I'm assuming nobody started. But in any event, do recall that we have office hours tomorrow morning, and then after class Thursday, and after class today, for that matter. Thea and I have the solutions, so if we forget how to do it, we can figure it out with you. Other than that, I actually started grading your project proposals because Matthew, finally, he ran into me in the hallway and he reminded me, and then I actually started. I told you guys I just need a reminder. So anyway, my goal is to finish that today. I have to take the T to Braintree, which is not a thing that I should have agreed to after work. So I will have a very long T ride to grade papers on. In any event, I believe your next project thing isn't due until the beginning of April, so you got some time. But do try to make some regular progress rather than like the quantized, every time I give you a deadline, you spend 24 hours before trying to make some progress. Questions, comments, concerns about logistical stuff? I think this class is pretty straightforward. The rhythm here is pretty rhythmic. Okay, so with that, we're going to continue our discussions today of inverse problems involving distances. So remember our story the last week or two, that was an intense squeaky chair, is something like the following. So we first talked about algorithms like fast marching and so on, which are basically techniques that are given a piece of geometry and then output distance functions, right? Like geodesic distance, shortest path, what have you. Then the last, I guess, two lectures, and we'll continue today, our task is sort of the reverse of that. Like we're given as input the set of distance values or relationships between points, and then as outputs, we're trying to come up with an embedding that satisfies that, right? And we talked about both some theoretical limitations and properties of this problem, right? Like for instance, 2 lectures ago, if you watched the online thing, you figured out that like you can't necessarily solve this problem for every possible distance matrix, at least for embedding into Rn. But we can do so with some wiggle room, right? That's the sort of takeaway of these hard homework problems that you all hate on your homework. And moreover, there are a lot of practical algorithms for doing that. So remember in the last lecture, we started by talking about MDS, which basically kind of reduces to an eigenvalue problem. And then we talked about some nonlinear methods, like this stress majorization technique, which is basically just least squares on distance, right? At the end of the day, that's all it's doing. You could have implemented it with gradient descent. Any questions about our story so far? Cool. All right, so far, I think you can sort of understand our previous lecture as, I'm inputting a set of distance values, and my output is an embedding into like Euclidean space, and the assumption is that my input somehow wants to be Euclidean. I just lost the embedding. But there are other applications where that's not the case, that like maybe my data set is like sitting on some curved manifold in space, right? And in that case, maybe I'd like to kind of unroll my data set before I actually plot it on the plane. So for example, very famous example called the Swiss roll data set, which is mildly useless in terms of an actual data set, but is the one that we all test on. The Swiss roll data set, I was going to draw it on the board, but I don't think my spatial reasoning is good enough, so I'll do it with my notes here. So in the Swiss roll data set, it's like 2-dimensional data, but it's kind of rolled up like this. We'll see it later on in our lecture. We have a bunch of points that are kind of sampled from some spirally shape in 3D, right? Now, if I do principal component analysis or MDS on a bunch of points that are sampled from this object, what dimension embedding would I expect to get? You're all continuing to nod, which is good. You're agreeing with the problem, but I'm asking for a number. Well, so this is a 2D object in R3, but like the algorithms we talked about so far, like if I did MDS, with a bunch of points sampled from this thing. And remember, I solved this eigenvalue problem. And once I start hitting 0 eigenvalues, I found my embedding, right? I don't need to compute anymore. How many non-zero eigenvalues would I expect in my matrix? 3, because this is a 3D object, right? But there's some universe, and there's a new class of algorithms, which are the ones we'll talk about today, where you say, well, really, intrinsically, like Jeremy points out here, no, sorry, Matthew points out, is we have a 2-dimensional data set, and we'd like to unroll it first, and then visualize that, right? In other words, somehow, you know, the relevant information for understanding this data is not just the Euclidean structure, and it's just a question of squeezing it into as low-dimensional space as possible, but maybe I actually want to do some geometry kind of edits to my data before I put it into the plane. Does that distinction make sense? Notice that this is where principal component analysis, if you remember that one from I don't know, linear algebra, machine learning, whatever, kind of breaks down, right? Because PCA would say that like the Swiss roll object is 3D. Like you just would not be able to find intrinsic 2D structure. Yeah, Marcel.
Can they be arbitrary transformations? Like, what are they based on?
Well, that's the question. That's sort of exactly what we'll talk about today, right? Like what transformations are valid and which ones aren't, right? Because I can make all data set, you know, any data set is one-dimensional if you believe in yourself. You know, you could just like throw out the whole data set, number them 1 to n, and now you have 1D data. But that's not a very structure-preserving embedding, right? And so typically we use this phrase, like what's the title of the lecture today, right? Like structure-preserving data set embedding, to kind of encapsulate this giant class of techniques where like you suspect that maybe there's either local or global geometric structure you want to preserve, and the question is how can you actually kind of translate that into math, right? Now, most of the algorithms we'll talk about today are the ones that are popular. These, by the way, tend to live in like the data science world. I don't know the distinction between that and machine learning, but there does seem to be one. A lot of these do not come with a whole lot of theoretical justification, and the history of these areas, they really didn't. More recently, folks in kind of manifold machine learning, this phrase, right, verifying manifold hypothesis and so on, try to go back and add some theory to this, like, you know, if I have some smooth object with bounded curvature and I sample it with some density, do I expect this algorithm to succeed? Those are really hard questions to answer. So those are largely outside of our scope for today. We'll talk about just some models people use in practice. But there's a whole lot of theory out there, I would say probably just waiting to be discovered. These are largely, like, I think problems that are out of the scope of what the theorists currently understand. I say that, and then you guys will send me 100 papers that tell me otherwise, and that's fine. Okay. So here's a different way to kind of understand what's going on here. So let's say that I have a data set. Here, this is a data set of 1, 2, 3, 4, 5, 6, 7, 8, oops, lost count, 9-ish points. And so far, what do our algorithms do? It kind of looks like the left-hand side, right? I've got 9 points, and I compute the distance between every single pair of them. So I've got all these lines crisscrossing every which way. And now from these distance values, I reconstruct my data set, and we kind of showed at least for MDS and Euclidean space, we can do that, right? But of course, if our data set really just looks like this set of points, right? I didn't get this set of distances, I just got this set of points. And my task is something like embedded in a lower dimensional space, like similar to MDS with not the full set of eigenvalues. Then it might be that the relevant structure is actually that these points kind of look like the letter C if I trace them just to their nearest neighbors, right? So that's the sort of perspective that we're going to pursue, that like maybe your local neighborhood gives you a different clue as to geometry of your data set than, like, for example, you know, the distance between these distant points starts to like make a rod that kind of pulls them together in some other fashion. Now, these are modeling questions, right? Marcel makes a totally reasonable point. Like, it may be that unrolling this data set is the wrong thing to do. Right? It completely depends on the structure of your data, what you're looking for, and so on. But there are many examples where there really is some interesting geometric structure just waiting to be found. There are all kinds of really corny synthetic examples out there you can find in the literature. Mostly because it's really hard to find a very clean example of a manifold in the wild. Like, things tend to get messy. But there are a few. My favorite data set was proposed from my, at the time was a postdoc, Roy Letterman, now is a faculty member at Yale, where they took a video where they took these characters from Star Wars, these little like plastic things, and they put them on carousels. And they had the carousel spin around at different rates, and they just videotaped it. So the data set is the set of frames where they forgot the ordering. And, you know, like Yoda is going like, you know, 10 miles an hour, and I'm struggling to think of a second character from Star Wars is spinning around at like 2.5 or whatever, but they shouldn't divide into each other in a good way. But if you do this long enough, if you think about it, it's sort of the product of 2 circles worth of information in that set of frames, right? So the data set, every individual data point here is like a frame in a video, so it's a very high dimensional object. But they can apply these manifold algorithms to like try and identify, in this case, this kind of toroidal structure that's in the data set, just embedded in some very high dimensional space. And there's lots of examples of that. There's another kind of well-known study, I think it's from Gunnar Carlson at Stanford, where they look at the space of like 3x3, 4x4, and 5x5 patches from natural images, right? So they just go through like all of ImageNet or something, like this giant database of photographs, and they just pick out, you know, like little grids of pixel values, like that, right? So these are like maybe points, probably 3x3 is a little too small. But 4x4, 5x5, whatever. So these are like little, you know, like 25 dimensional points. And they want to, in that case, this is an example in the sort of computational topology community. They want to kind of understand like what is the manifold structure sitting underneath the space of image patches. And they find there's a totally reasonable one because it tends to be that natural image patches either are totally flat or they just contain like an edge. Right? And so that edge can kind of rotate, which kind of gives one axis of kind of interesting ways that the data varies, or it can get lighter and darker. And so there's like some interesting kind of low dimensional structure hiding there. But anyway, these are two examples of many where people are trying to find interesting manifold structure in their data, but the data itself is not just flat. It's not Euclidean. There's some curved structure in there that we're trying to unroll, right? Now, as usual in this course, we kind of ping pong between theory and practice a little bit, at least kind of quote some of the relevant theoretical results. In this case, you have to be a little careful. Indeed, like if you look at the really classical stuff, you know, like a Whitney embedding theorem and later on, you know, Nash embedding theorem, at least for like Riemannian manifolds, you actually can always embed in an isometric fashion as long as you have a high dimensional enough embedding. But the embeddings start to look really wild. I don't know if you've ever spent some, this is totally outside of the scope of this course, but if you're bored and you feel like reading about the Nash embedding theorem, essentially what it's saying is that you can like embed Riemannian manifold into a high enough dimensional space, but the embeddings you get are like these like weird riffled objects. Like they're not, you know, it's like a really bizarre construction. So it's like doesn't translate well to an algorithm. But anyway, there's some cool theory out there, and really nice visualization that like, for instance, here is a, do you guys know what a flat torus is? No? It's a Riemannian manifold, but it's not one that we can, well, we can embed it, but not easily. So here's a flat torus. You take a square, and you just glue the top, and you glue the sides like that, just like a torus. The only difference is that you say this whole thing has curvature 0. It's flat. You might not believe it, but it is, so you can see it. I drew it. It's on the board. But you kind of add boundary conditions that glue the sides together. This is a perfectly valid manifold from a Riemann perspective, but it's not embedded in Euclidean space. Obviously, the edges are kind of doubled here. And so if you kind of follow through this theory and try to embed it in R3 or R4, you get this really crazy ruffled shape, which is the thing that's embedding it without a boundary, right? Let's see. Yes?
So this is an embedding in R3?
That's right. Although in general, this theory would say you have to embed in R4, right? Yeah.
This is curvature 0 everywhere?
I believe, but it's like sort of a fractal kind of thing. Like it's like literally taking origami and like bending it forward and backward and forward and backward and forward and backward to kind of simulate curvature. These are not nice surfaces. Yeah. Anyway, so that is well outside of the scope of what we'll do in this class. Here we're given some data set, and we're kind of assuming it's sampled from some smooth object, and we're just trying to recover the nice structure here. And this is a task that goes back as long as data visualization. Like, this is a suspicion lots of people have had about their data sets, and if you started from principal component analysis, I think is a totally reasonable next problem to consider, right? So we'll talk about some of the classical models for doing this because they actually build a lot on our previous lecture. But again, remember our previous lecture says I have a distance matrix that I think is Euclidean structured, and my task is just to embed it. So a lot of the algorithms out there for embedding data sets that are curved, the first thing that they do is they try to convert that into a distance matrix, and then they just use one of the past methods to embed it. Okay? So let's see a simple example of that. Here's one. It's called isomap. Has anybody played with isomap? It's like in Python. It's one of the little data science tools. Yeah, a few of you. Isomap is an extremely simple algorithm, and it does the following. So essentially, you're given some data set, like, aha, here's the Swiss roll. You can see it looks like a twisted up sheet of paper. And OK, so we have a technique, namely from our last lecture, we have MDS, which takes a distance matrix and tries to embed it. So all isomap is going to do is try to extract an appropriate distance matrix for MDS to use. And so in particular, what it does is you take your point cloud and you construct a k nearest neighbor graph. So for every vertex, like every data point here, you just create an edge between that data point and other ones that are nearby. Hopefully we're all familiar with what a k and n graph is in this class. Is that okay? Cool. And now, for every pair of vertices in that graph, I compute the shortest path distance in that graph. Probably weighted by distance in R3, or Rn. Does that make sense? So now, between every pair of vertices on this Swiss roll data set here, I have a shortest path, but my shortest path is constrained to move along the graph of data points that I have here, right? It can't, like, I don't know, it's not just a straight line anymore. Okay, so this is just graph-based, like Dijkstra algorithm. Many of you may be familiar with Floyd-Warshall. You know, if you're ever stuck in a programming contest and you have to compute shortest paths, it's like 5 lines of code. So you do that to get like an n by n matrix of distance values. And now those distances, I mean, if you think about it, they're kind of, like in this case, planar structured, right? This kind of looks like shortest path along this sheet rather than shortest path in 3D, approximately. Yes?
What if the poles were close enough that one of the points?
It's a good question. We're going to come back to that. So we're going to take that pairwise distance matrix and embed it, maybe with the original isomap used MDS. Obviously, you could take any algorithm from the previous lecture here. And what you get out is an embedding of your data set. Yeah? Does this algorithm make sense? Okay, now Marcel asked a totally reasonable question, and it's sort of the downfall of this technique and many others. So K&N graphs in general are quite noisy. I mean, data set, okay, this is like a really beautiful example where like somebody clearly synthetically constructed this data set, but you know, most data has noise. Not all, but most. And so for example, you could imagine a universe where there's some Gaussian noise about the surface here, and so maybe there's just a few points that are kind of scattered in between these two sheets. Well, that's wildly problematic for isomap, because let's think about what can happen. So I've got this kind of spirally structure to my data. Here's my profile view of my Swiss roll. I don't know if it's actually, Anna, is this Swiss food? Do people in Switzerland make these things? You guys are, you know, people that have spent time there? Americans call these things Swiss rolls. It's like this, you know, it's this like sponge cake you kind of roll around.
We have them in Norway.
Norway. Okay, so in the Norwegian roll data set here, let's say that we accidentally created just one spurious edge. It could happen. Or maybe like there's just one noisy point here, so you kind of get two edges like that. Think about what happens to your pairwise distance matrix now. It drastically changes just because I made one bad edge, right? Because now, probably the shortest path between everything here and like this entire region is going to cut through that bad edge, right? And so this isomap algorithm works well for like very densely shaped data sets, but if I have a spurious edge like a sample, then suddenly it'll fail pretty drastically. Like not just, like, and this is not something that fails elegantly, right? Because one bad edge will break this whole matrix. Yeah. So that's a good point. And we'll come back to that and see how we can fix it in a bit. To add a little bit more detail here, here you do need all pairs shortest path. Yes, Dustin.
Could we do like something like edge disjoint shortest path and then take something like the 10 edge disjoint shortest path or something like this to make it a little bit more robust?
That sounds like a fantastic heuristic, and I don't know what edge disjoint shortest path is, but I believe in it.
Or like multiple shortest paths,
Yeah.
and all of them needs to be edge disjoint or vertex disjoint.
Oh, I see.
And if you have like one shortcut,
That's true. Yeah. I mean, there are ways you could try to fix this distance function and make it more robust, for sure. That'll add some computational costs. It's already pretty expensive, right? You have to compute this big, dense matrix of distances. Yeah, there are ways to fix this. I don't know. Be a good course project to experiment with a few. To add a little detail here, if you want all pairs shortest path, fun fact, you can do it in like 6 lines of code, but that's the thing that you probably all encountered before. Another thing that's worth noting, at the very least, we can maybe reduce the computational cost of isomap a little bit. Remember, we talked about landmark MDS in the previous lecture, which says I kind of do embedding on a subset of my data, and then I infer it from the rest just using a formula. And I can do exactly the same thing here, because remember, landmark MDS just needed sort of the distance of the new point to the landmarks. So I could kind of introduce a new point into the graph and compute its shortest path to the old guys. And then basically use an identical formula to the previous lecture. up to sign, because I think I got the sign wrong last time. Yeah, and at the very least, this reduces it from like n cubed or time to like something slightly less. There's nothing terribly insightful here beyond just like you can cut out some data points and then your problem becomes faster. Yeah, but these are just some standard techniques. Okay, so I would consider isomap to be a very global method, right? Like it's still trying to preserve every single pair worth of path distances. The only difference is the distances are coming from along the surface or along the manifold rather than extrinsic space. Does that make sense? Like essentially you're just kind of doctoring the input to MDS rather than messing with the algorithm itself. Always, when people teach isomap, it gets paired with a second algorithm. I don't know why. I think it's a historical thing. The second algorithm has a very similar set of theoretical guarantees, which is to say, not very many, but sort of has an opposite perspective. And that's a technique called LLE. Now, a few of you have played with isomap. Has anybody played with LLE? Yeah, interesting. It's a disjoint set. Fascinating. Right, so isomap and LLE are both algorithms with the same end goal, which is like you have some high-dimensional data set, you think it's maybe curved, and you'd like to embed it in a lower dimensional space and unroll it all at the same time. Right? Now, isomap, the way that it did that is it tried to estimate pairwise distance between every pair of points on this high-dimensional manifold. LLE tries to do something a little more modest, which is to say that for every point in my domain, maybe the way I should think about it, like if I unroll something, you know, like what stays constant and what changes? Well, what's changing is the global structure, right? Like for instance, you know, if I bring the edges of the sheet of paper together, then clearly like these points got closer. I'm not saying anything too exciting. But what remains kind of consistent is local structure, right? Like what I'm not messing with is the fact that like, you know, if I drew a few points on the surface, the set of neighbors probably wouldn't change as I unrolled this very much, right? And so LLE applies that intuition to derive a different kind of embedding technique, okay? So here's how LLE works. It proceeds in kind of 3 steps. The first one is the same as isomap, which is compute that k-nearest neighbor graph. A lot of these algorithms do that because that's sort of our proxy for like the underlying manifold structure for your data. There's a reasonable question there, which is that a good proxy? But we can ignore that for now. And now there are 2 steps to LLE. There's the analysis step and the synthesis step, or embedding is also fine. So in the analysis step, we're going to kind of put an additional structure on our point cloud. And then in our embedding step, we're going to use that structure to recover a lower dimensional embedding of our data. Okay? So let's add a little bit more detail here. So, right. Chalk. Okay. So the first step is going to be to do analysis here. And essentially, when we do the analysis step, our goal here is going to be the following. So we're looking for local structure. And the way that we're going to do that is we're going to have all of our xi's and all their k-nearest neighbors, right? So I've got some vertex, then I've got like a few other neighboring vertices in our data set, right? And what we're going to try and do is we're going to write each xi, so like every point in my data set, as a weighted average of its neighbors, approximately. Right, so the idea here is like I've got my data set, I collect my k-nearest neighbors, so like here's, you know, my one ring like that. And so rather than preserving all the distances, what I'm going to try and preserve here is the fact that this guy is like kind of close to this point, a little farther from that point, and so on, like that kind of a relationship. Does that make sense? Let's translate this into math. Okay, so in particular, our unknown here in the analysis step for each vertex I is we're going to compute a vector which in my notes is labeled omega. And these are like the averaging weights of my neighbors. So if I'm doing k-nearest neighbors, then like omega I can think of as being an arc. For those of you who have heard of barycentric coordinates, this might be a very familiar story to you. Pause there for a second. Okay, so in particular, we want kind of two properties for the omegas, and then Anna's going to tell me the property that I'm missing. So, right, so our first property here is that I want my point at the center, we're thinking of it like kind of a weighted average of its neighbors, right? So maybe I do the following. So I'm going to try and use our usual notation. By the way, I think in my notes and even on the screen here, I got lazy and dropped the subscript I at some point, but we'll just assume it's always there. And let's say that n stands for neighbors, right? So the idea is I want to write my center point here as some weighted average of its neighbors. In this set, I am not going to include x in the neighbors, because if I did, obviously, I would just put 100% on x. That makes sense? Now, usually when we talk about weighted averages, we make a second property here, which is the sum of omega I j over j is equal to 1, right? Because this is a set of averaging weights. Now, in the original model for LLE, these are the two properties we had. What am I missing? Yeah, like usually our averaging weights are positive. You actually could totally bake that into this model, and I was thinking about this morning as I prepare my notes, and I actually don't know why they don't. I guess computationally it would be a lot harder, but it would be kind of a fun experiment to try. Okay, especially now that like we have, when this thing was written, I forgot to reference it, it would have been like the 70s and 80s, like convex optimization wasn't as common as it is now. There are pretty easy algorithms for projecting onto this simplex that just didn't exist back then. So it might be interesting to kind of reconsider. Yeah?
But I think now if you don't constrain it to be positive, you can also have like an offset. If say all the neighbors are in one direction, then you can still extrapolate.
That's right. Yeah, which is kind of needed here, right? So the comment was like, you know, what if my data set like has an edge? I think in general these algorithms don't work terribly well in this case. And like I have some data point here, then my k nearest neighbors are all going to be kind of pointed inward. In this case, you actually would expect, as you say, that you probably would want a negative weight. If you look at the schematics they use to illustrate this algorithm, they never include that case. But you're right, that would be boundary case where you really would want something else. Yeah. Okay, so we'd like these averaging weights. You know, a fun course project would be to add a third property here, which is they're positive, but they don't, so we won't either. Okay. And now, in general, we have to be the tiniest bit careful about dimensionality here. So usually the assumption is that the dimensionality of our data set is larger than k, like the number of nearest neighbors that we choose, because otherwise this becomes underdetermined, right? We're going to need more conditions to tie break. Like for instance, if I'm in the plane and I have 10 nearest neighbors, there's a lot of way to write me as a weighted average. Yeah. Then you need generalized barycentric coordinate. Okay, so, but in the high dimensional case, we can write down an optimization problem. So we could do the following. We could optimize over omega. I guess I should write omega I. The following, I could say xi minus the sum omega I. Sorry, I'm translating my bad notes into better notes. Like that, subject to that they sum to 1, like that. So this is kind of a reasonable model for how to compute the omegas. Okay? Whew. Now, we're all grown-ups here. We shouldn't be using indices like this. This is always a sign that we've done something wrong. So let's put this into matrix form. So in particular, I can make a big, actually no, we're going to leave xi as just a single x. Usually the way this is implemented, by the way, is you really do iterate over every vertex. So you kind of do one vertex at a time. But we can think of omega at least as a vector, right? So maybe we think of n as kind of like this, you know, the set of neighbors, like that, and omega as a vector, right? So then really, what is our optimization problem? It looks like, all right, fine. It looks like the following. So we're going to take the min over omega of n, omega minus x. Again, there's a lot of I subscripts that are missing here. Subject to the sum of omega is equal to 1, right? So this is just fancy notation for the thing we had on the top. So how should I solve this problem? Lagrange multiplier. Yeah, Anna's absolutely right. This is something I can just write a formula for. Right? So in particular, if we introduce our Lagrange multiplier lambda here, should I go through this derivation or should I just spoiler alert and give you the formula? I think we can probably do the latter. So if you are not comfortable with Lagrange multiplier, you should at home justify the following, which is that the optimal solution to this problem is as follows. You solve a linear system of equations for omega and lambda, which equals n transpose x and 0. Notice that this, that's a 1. I think. Yeah, my notes are wrong. Okay, so notice the second row of this thing is easy, right? This is saying the sum of omega is 1, right? And the first one kind of feels right? This looks like least squares. Do you see that? You have like an n transpose n and an n. This looks like a normal equation. So I'll let you guys double check this one at home. But the good news is this is a relatively small linear system of equation. Usually when you're doing k nearest neighbors, k is like 5 or 10, right? And so in this case, like essentially, the point here is when we do this analysis step, we have this very parallelizable piece of code that just iterates over every vertex of our k and n graph and then solves a linear system of equations of the same size. So this is a thing we can do relatively quickly. Does that make sense? Fantastic. And so what that's going to lead to, we're going to make a matrix W. And we're actually going to put this in, what letter did I use for the size of my data set? Did we give that a name? Let's give it n. We're going to make a matrix W, which is not in k by n, but is n by n, where essentially every row of W is going to be kind of like the W computed here, but then the indices we'll use correspond to the indices in the full set of data points. Does that make sense? Okay, so that concludes our analysis step. So what did I do? Essentially, for every single point in my data set, I wrote it as roughly a weighted average of other points in my data set that are nearby. That's, from a high level, that's what just happened. Does that make sense? So a way of expressing that is the following. If x is my data set, so the columns of x are all my data points, then I could say that this is roughly equal to x times w transpose. The transpose is for technical reasons. You've got to be careful with rows versus columns here. Does that make sense? So this is like the thing that's taking weighted averages, and this is the original data set, and those two are kind of the same. Okay, everybody understand the analysis step? Essentially what it led to is this matrix W. Okay, so the next step is embedding. I'm writing really big today. I keep running out of space. Okay, so that's okay. We actually don't have a whole lot of math to do today, for once. So now let's do the embedding step. So in our embedding step, what are we trying to do? We're trying to kind of design a lower dimensional data set with a very similar structure, right? That's our goal here. So now we're doing embedding. Like that, okay? And essentially, now we're going to kind of forget x and just work with w for a little bit, okay? So now what we want is going to be a new embedding y, and y we're going to say is maybe in p by n. So remember the columns of y are going to be like the embeddings of our points in the lower dimensional space, but p is going to be like this, like the unrolled dimension. So chances are we would think of p as maybe a lot less than, I don't know, like m, like the original dimension of my data set. Okay? I'm making up letters as I go along. Everybody get the idea of like our goal here? Now, what might be a good property for y to satisfy, given the analysis we've done so far? Like, what would make for a good y? Yeah.
Close to satisfying the property that you use?
Yeah, Marcel's awake today. This is great. So, a good y might be one where, well, if we're trying to preserve, I don't know why my font changed. If I'm trying to preserve structure for the original data set, maybe I want y to also have this property here, right? So in other words, like the set of my nearest neighbors roughly doesn't change when I unroll my data set. Notice that x and y are not identical because y is in a lower dimensional space. That make sense? Okay, So kind of continuing the logic that we had before, maybe I phrase a least squares problem. I say, okay, great. So I'm going to find a y with a, so I want y minus y w transpose to be small. So I write a least squares problem. This feels reasonable to me. What's the solution to the problem I wrote on the board? 0. And notice that 0 actually, it does everything we set out to do. It keeps you very close to your neighbors, right? So unfortunately for us, we need some constraints to make the solution to this problem non-trivial. A different way of putting it is that weighted average property is sort of scale independent. Like if I take my data set and I scale it up and down, I'm still the same weighted average of my neighbors. Yeah? So the way that LLE gets around that is by adding a constraint. So for one, we will take our data set and we'll just make it sum to 0. This is just like we had in the previous lecture. This doesn't do much but beyond just like get rid of this extra degree of variability that we don't really care about. And the second thing it does, which is a little more sneaky, is the following. It says, okay, we can say y times y transpose is equal to the identity p by p. Okay, so if you think about it, what's going on here? Essentially, it's looking at all of the coordinates of the y's one by one and making sure that like the x coordinate, the y coordinate, like each first coordinate, second, the third one are all different from one another because their dot product is 0, and moreover, they don't do anything boring. Like they have to square add up to 1, so you can't just have something collapse. Again, is there anything like super canonical about this choice? No, it's just some way to avoid stuff collapsing in on each other. Okay. All right. So let's do a little bit of math on our objective function. So notice that I could have factored out a y here. So this is really the same as the norm of y times the identity minus w transpose, like that. Everybody agree? Yes?
What confuses me here is in y transpose, don't we take the inner products along the dimension n?
Yes.
So in which space are these inner products then?
The inner products are in the high dimensional space, like over all of the points, right? Because if you think about it, what it's trying to say is that we don't want all the points to end up in the same place. So yeah, so this is a small matrix, so it's a small number of inner products in a high dimensional space. If you did y transpose y, it would be over-constrained, right? It would be a lot of inner products in a low-dimensional space. Yeah. Cool. So let's take our objective function. So that's the norm y times identity minus w transpose for Penius. And in this class we basically have one trick, which is just like expanding squares of things. It's like the only thing we know how to do. Yeah. And this is squared. The only annoyance is this is a matrix norm. But remember, we have a little trick for doing that. This is the same as the trace of y times the identity minus w transpose times this whole thing transpose, right? So identity minus w y, like that. Hopefully I did that right. I think so. And notice that this thing, right, this is just a byproduct of the analysis step, right? Like this is a constant. So let's call it m. Done. Okay, so this whole problem here, the objective function really is the trace of y m y transpose, like that. Okay? So we have a homogeneous quadratic objective function for our problem, right? There's no linear term. And we have an orthogonality constraint for y. Is anybody really good at Lagrange multipliers in their head? Can guess what'll end up happening here? M is a symmetric matrix, if that helps. Rhymes with eigenvalue. Yeah, this is an eigenvalue problem. So essentially, at the end of the day, what this is showing us, so again, this is really our objective function here, is that we want, let's see, this is a minimization problem, so it becomes the p smallest eigenvectors of the matrix M with non-zero eigenvalue. Okay? And so essentially, you should check that at home. This is just another Lagrange multiplier argument. There's a lot of those we're skipping right now. But at the end of the day, this LLE algorithm boils down to two steps. The first one is a bunch of little linear solves. And the second one, you have this big matrix. You do a matrix multiply to get M. And then you compute eigenvalues. Yeah? Incidentally, if you're really good, you could probably do this without finding M. You could do it from the SVD of this matrix instead, but I always get that wrong. Any questions about that? Like, so from like a million miles away, again, what goes on in this algorithm? Like, we have our data set. This is a bunch of points scattered in space. For every point, we gather its neighbors. We write that point as roughly an average of its neighbors. And then we find an embedding, so a lower dimensional set of points, with the property that those things also are the same weighted average of their neighbors, just in a lower dimensional space. I see a few furrowed eyebrows. How can I help you all defurrow? Yes?
So I'm confused by the constraint YY transpose you say that. I mean, I agree that we need something that makes it not.
Yeah.
Isn't it more natural to say, let's say, the Frobenius norm of Y is 1 or something like this?
The Frobenius norm of Y being 1. What you'll end up happening in that case is funny. This is one of these things where if you, one thing I encourage you to do is to write down all the alternatives you can think of and then convince yourself that they don't work. So like, for instance, if I just constrain the Frobenius norm of Y, then one thing I can do is just like make all of the rows of Y identical to one another, which you don't want, right? Like essentially this becomes essentially the reason you need so many constraints is because you want every single coordinate to be informative here. Yeah, it's definitely a heuristic what they did. I think in fact, if you look at the history of this algorithm, probably what they really did was they just computed eigenvalues of M and didn't worry about where this problem came from, and then reverse engineered like, oh, see, it's optimizing. But it's a pretty reasonable technique. A different way of putting it, I see your hand, is like if you think of that MDS algorithm as sort of using eigenvalues to extract an embedding, this is really doing the same thing, but it's in the other end of the spectrum, which kind of makes sense because distances are like big values and similarities, like what's in W, are kind of small. So there's sort of reverse problems of one another. Yes, Anna.
Is this a bit like, I mean, just minimize Y minus Y W.
Uh-huh.
It's kind of like a weird Laplacian with the weights of the neighbors given by this W.
Yeah.
And then you're kind of saying just like flatten down my.
That's 100% right. This thing is exactly a Laplacian operator, right? Notice that I subtracted W from identity, yeah? So that's absolutely a different way of understanding these things. It's a spectral embedding technique. Yep. For those of you who don't know what that means, that's okay, because starting in our next lecture, we will be doing Laplacians in so much detail that you will never want to write a triangle on your math paper again. Yeah. Fantastic. So let's compare our two algorithms so far. We have two, right? They're LLE and isomap. And somehow these are two algorithms for the same end that are using two very different structures, right? One is like local geometry, right, like LLE. The other is very global geometry, like isomap. Yeah. Qualitatively, they often behave similarly, but sometimes they don't. Actually, before I flip the slide, can anybody think of a good counterexample when these two algorithms would do very different things? There's a really clever one that I like in the literature. In fact, I'll draw you the counterexample, and then maybe you guys can think for a second before I flip the slide about why these two things would behave very differently. So let's say that I took my Swiss roll data set. I'm going to, and I unroll it, and then I'm going to re-roll it again, just because I only know how to draw things on the board. So I unroll my Swiss roll, my Norwegian roll. There it is. See, it's unrolled. I guess like sushi also, possibly. But usually, I guess it doesn't wrap more than once. OK. And now, here's what I'm going to do. I'm going to really screw up the Swiss roll functionality because I'm going to punch a hole, so the jam is going to fall right through it. So there's like a little void. So now this thing looks like a I don't know, torus, whatever, a annulus, that's the word I'm looking for. And now I take this thing and I roll it on itself just like I did for the Swiss roll. So I like basically took this sheet of paper, I punched a hole in it, and then I rolled it about itself, okay? And now I'm not going to be able to give the rest of the lecture. So, what do we think will happen with isomap and LLE here? So remember like what isomap does, right? We've got a bunch of like sampled points on this object, right? And I compute graph shortest paths on this thing, and then I'm trying to reconstruct those on the plane. Yeah? Anybody have any intuition? Like, does isomap give me my unrolled Swiss roll? Yeah. Okay. That's a good idea. So let's say I look at these 2 points. and I compute the shortest path in my KNN Swiss roll. What's the shortest path? Well, it's going to like cut around the side of this hole, something like that. But remember, this is the distance that isomap is trying to embed into the plane, right? So in particular, in fact, let me bias it a little more. Let's say that I, only for purposes of drawing things on the board, here's my unrolled Swiss roll. And let's say that I cut a really long, thin slit like that. So now the distances between these 2 points need to get a lot bigger. So when I embed it into the plane, isomap is going to do something crazy. Like it might take the edges, I always get this wrong. I think it'll bulge it like that. So that these points are far apart when I have my planar embedding. Does that make sense? Or luckily, your instructor is bad at drawing, but conveniently he did the computation, and we can compare the two. So here, we've got different data sets, and then let's see. We have a lot of different algorithms actually, but there's isomap is on the upper right, LE is on the lower left. LE also can just make some distortion, like for instance, at the boundary, like we were asking about before, LE can have some funny behavior and like pinch and so on. But I think the most obvious issue here is if we look on the right, I think it's really cute. These people call it the Swiss hole data set. No, fine. So in the Swiss hole data set here, notice that they've kind of like taken this little rectangular chunk out of the data, and when you embed with isomap, notice that it like punched a giant hole in the embedding. Whereas like LLE has different problems because it struggles with the boundary, but the interior structure is roughly right. Yeah?
I'm not entirely clear on why I would have to do that. Why couldn't it just do the...
Well, because remember what isomap's goal is. It's given a distance matrix, try to embed it into the plane as much as possible. So from isomap's perspective, these 2 points are really far apart. They should not be this close in the embedding.
Oh, I see.
Yeah. So that's the main difference here. So these are qualitatively different algorithms. It's funny because they get used for the same task very, very frequently. Okay. Cool. Now there's so many options out there for different embedding methods, and they really run the gamut from like just trying to like compute some version of isometry into your space, which is roughly what we've done here, to like doing more complicated stuff. Like on the very other end of the spectrum, maybe is like the people in computational topology that like don't care about geometry at all. They just care about connectivity, and then obviously there's a lot more wiggle room to optimize in. Another one, I want to give you a buzzword now, just so that you don't accuse me of not forgetting one of the main classes of embedding techniques, but we're going to defer it until we know what a Laplacian is a technique called diffusion maps. This was the most popular thing to study in applied math when I was a grad student, and these days probably nobody remembers it. No, that's not true. Diffusion maps essentially embeds points, again using an algorithm that looks like MDS, but just applied to a different matrix, which is like heat kernel, like diffusion distances. So what they do is between every pair of points, kind of measure like how easily does heat diffuse along the manifold from one to the other. This is a thing that mathematicians have developed lots of machinery for approximating, and then use that object to embed. So once again, you just use eigenvector for the embedding. I encourage you to read this paper, especially like you've got these reading assignments in this course. I hope you're not forgetting. This is a good one to read. Like it's a very clean and clever idea, and it really was like one of these foundational papers in applied math that just led to this entire branch of research. Another thing I should note, by the way, is that people in computer graphics apply exactly the same kind of algorithms, just restricted to 2 dimensions. And in fact, the earliest versions of algorithms for this task I'm illustrating here were precisely isomap and LLE. In computer graphics, a very typical task is to take a 3D surface and then map it into the plane. This is called parametrization. And it's used a lot, for example, for texturing. So like maybe I have a 3D triangle mesh and I want to store, like for some reason I'm painting my octopus with a checkerboard. Obviously artists didn't write these papers. But when I do that, I'd like to store this very high frequency texture, so I do that on an image, right? And so the way you do that, you take the 3D surface, you kind of squash it onto the plane, store the texture on the plane, and then map it back out, right? It's called parametrization. And if you think about it, it's exactly the same problem here. It's just that p equals 2, yeah? The other difference between parametrization and this more general embedding problem is that triangle meshes have triangles. They have interiors. And so the distortion energies that they can use are slightly tuned to that, but only slightly. Like, I mean, if you look at our previous lecture, right, we talked about stress majorization, where essentially you have this graph of neighbors and you just want distances on that graph to be kind of preserved in your embedding. If you look at most energies that get used in the graphics literature, for example, here's a big table of them, which is in a recent paper with an algorithm. This paper is really nice, but actually my favorite part of this paper is just they did a really good job of tabulating all the objective functions people use in this area. They're very similar to stress majorization. All it's doing is like different ways of measuring that the edges of your triangle mesh don't get distorted too much in the plane. Now, in this class, we don't have time to cover some of the more detailed aspects of this specific problem. There are additional challenges, namely, if your triangles flip over or they squash into a point or something like that, then your parametrization isn't very useful. And so, like, the algorithms we cover here cover parametrization up to about 1998. Then the past 20 years of 25, 30 years of research in this area have been dedicated to like the aspects of this problem that make it a little more special for computer graphics. Actually, I guess let's give it a little more credit. Like this algorithm, spectral conformal parametrization, which is roughly that in graphics, was I think 2008. So it's not all that long ago, I think. You guys weren't born yet. This is the part of lecture where we're just going to give you a bunch of like kind of pointers to other interesting problems that are related, but not talk in as much detail. Another one, if you want a really, really hard problem, is embedding from geodesic distance. So like, let's say that I have a surface or a manifold more generally, and I have the topology of this thing. So like I have a triangle mesh of a sphere. And now between every pair of vertices on that mesh, I tell you I want an embedding where the geodesic distance along my embedded surface has some prescribed value. So there are very few algorithms out there for solving that problem. It's different because now you're talking about geodesic distance, right? It's the distance along the surface. And these are very hard problems to solve in practice. They tend to be numerically stiff and hard to do. This was one early technique from the Bronsteins. And then later on, actually, I think Albert Chern, who's now at UCSD, has some interesting work that tries to embed things from metric, and you could view his research as sort of a much better modern version of some of these old techniques. In terms of, so these are on the very computationally expensive side. You could ask the opposite, right? Which is like, what if I don't have time to solve an eigenvalue problem? I can't do any of this stuff. Like, are there reasonable embeddings I could use that capture manifold structure without having to do a bunch of optimization and computation? And the answer is like, obviously you can't do as well as the algorithms that we've talked about, but you can do something. So for example, a very reasonable thing that people have done is to basically embed points by just using their distances to other points, like just that vector of distance values. And in fact, if you remember 2 lectures ago, that was roughly how we started, right? That was, I forget the name of this embedding technique with relatively low distortion. This is the one that you'll check on your homework. And the funny thing is this keeps getting proposed and reproposed in the literature over and over again. So actually, I was just looking in 2023, there's this ASIF embedding algorithm. It's going to appear in iClear, so I guess it hasn't even appeared yet. And once again, they do something very similar. So this is a fun task where like, I have maybe a big data set of images and captions, right? And now I get a new image and I want to caption it, right? And so the way that they solve this problem is they just borrow somebody else's caption. And so the way that we're going to do this is there are really good tools for embedding images, like you know, these things on Souped Up. There are really good tools for embedding captions. And so we kind of co-embed these things by looking at distances in the 2 spaces. So you kind of like, let's see, how does this work? So now I get a new image, and I embed it by looking at its distances to all the other images in the data set of paired things. And then I basically use those weighted averages, just like we might do in isomap here, or LLE rather. But I just use those same averaging weights, but now in the text embedding space to kind of infer where my position would be in that space, and then kind of back out to find a caption. Anyway, the details don't matter a whole lot here, but it was kind of funny to look at this paper and realize like it's just a reincarnation of the same kind of techniques. The more things change, the more they stay the same. Okay, so our takeaway so far is that there's just a giant zoo of different embedding algorithms. And You know, I think it's valuable to actually read the docs here, like understand that these are things that behave very differently qualitatively. And depending on your data set and the particular tasks you have at hand, one may make more sense than the other, right? Like maybe you don't trust your local structure, maybe you do. In practice, I think what do people do? Well, none of these algorithms are particularly expensive, so you just try 10 of them and you look at the embedding you get and see which one works best. But of course, we can logic our way out. Now, for the last couple of minutes of lecture, I thought I'd just point you guys toward other problems in this domain in case this is an interesting thing. Starting in our next lecture, we're going to do something very different. There are all kinds of really fantastic problems in the area of computational metric geometry. This is such a fun area of research. It like sits right at the intersection of optimization and geometry and probably other things I'm not thinking of at this moment. And so I thought I'd highlight a few other problems that are fun to study. So here's one, for example. So this is the metric nearness property, or metric nearness problem, rather, which has the following. So let's say I want to run an algorithm like isomap, LLE, MDS, whatever, and that algorithm, obviously only loosely for the things we talked about, is predicated on actually having a distance matrix as input. Now, distance matrices have properties. They're positive, their diagonal is 0, and they satisfy the triangle inequality. But a lot of times, the data that we get doesn't really have that structure. So for example, there are all kinds of like funny psychological phenomena. Like if you give people photographs of things and ask them to measure similarities or distances, they tend to give you distances that don't satisfy triangle inequalities. Like everybody thinks everything is close to everything else. So because of that, totally reasonable computational problem would be to input a matrix D and then output another matrix X, which is an approximation of D, but as a hard constraint, has a triangle inequality built into it, right? So find me the closest matrix that is truly a metric and approximates D. Incidentally, this is a convex problem, right? So the objective here is convex, right? It's just least squares. And the constraints are all just linear inequalities. There's just a lot of them, right? For every single triplet in X, I need a triangle inequality. So you could put this thing into your favorite linear program solver, or quadratic program solver, I guess. The only problem is it would take roughly the rest of your life to solve such a thing. So there's all kinds of specialized algorithms for specifically this problem. So here I've pointed you toward a paper from NeurIPS in 2004, which is really nice because the whole paper kind of fits into this little box. Essentially, all the algorithm does is it just keeps looking for violations of the triangle inequality and then just fixes them. And you can prove that this, if you construct this algorithm very carefully, really does converge to the solution of the optimization I've written for you there. So this is another example of a problem in metric geometry. You could imagine that some people maybe use a technique like this to pre-process the input for LLE or isomap or whatever. Yeah. Here's a different problem, which is matrix completion. Maybe I have a few distance values and I just want to infer distances between everything else. Notice that these all fit nicely into convex optimization kind of universe. So here, you know, I mask out a bunch of entries of some matrix. Maybe it's the gram matrix or the distance matrices, right? Those are kind of equivalent. We argued that. And so I'd say, like, you know, masked, I'd like P naught and P, like the pairwise square distances, to be similar to one another. But I want to make sure that this guy also has a triangle inequality and everything else. And it turns out you can kind of reduce this to a semi-definite program. So we're not going to go through the details here, but I've given you a nice reference toward this technique. This would be matrix completion, where I have a pairwise distance matrix and then I forgot some entries and I want to find the rest. Finally, one problem that we will cover, because it's on your homework a little bit, is something called maximum variance unfolding. And this is basically yet another embedding technique when I have only partial sets of distances, but I trust them pretty well. Okay? So in maximum variance unfolding, essentially my input here, okay to erase? I think we're pretty far past this. This is a fun algorithm, by the way, to, like occasionally in this class we get students of Pablo who know something about semi-definite programming or you know, from that side of our department. There's all kinds of interesting analysis to be done on this particular technique. It looks something like this. So let's say that I have, in maximum variance unfolding, I have a bunch of triplets, I, J, D, D naught, I, J, which is just saying that like point I and point J are this far apart. And my task, once again, is embedding. But now maybe I don't have enough of these that I can't actually write down that eigenvalue problem from before. So for example, let's say that I have 3 points. And I just know the distance from point 1 to point 2 and point 2 to point 3. But nobody gave me 1 to 3. And now there's a problem, of course, which is that like I could basically hinge about this vertex, right? Anything on that circle is an equally good embedding, even if I have a hard constraint. By the way, there's like a soft constrained version of this problem, but like, yeah, for today's lecture, we won't worry about it. Okay? So in maximum variance unfolding, it's kind of an interesting idea. And the basic thing is like, I have these distances, and maybe I'm trying to embed them, but I actually don't know what space to embed them in. I don't know how many dimensions I really need. Okay? And so one thing that I could do is I could say, well, in the absence of any other assumption, I should kind of maybe find the dimensionality of my embedding that's as low as possible, okay? And so take a look at this picture here. So this is the simplest version of MVU. I've got literally 3 points, and they're hinging about a shared vertex. And if I think about it, what's sort of a special configuration of these points? Well, if I hinge and make a 180-degree angle like there, then suddenly, rather than having a shape that like looks like 2D, right, like a two-dimensional object, if I did PCA on it, now it's a one-dimensional thing, right? They all sit along a line, right? And so in maximum variance unfolding, the kind of interesting idea is that by maximizing the variance of your embedded set of points, notice that this is also the most spread out configuration of these things, so this tends to lead to a lower dimensional embedding of your data set. So it's kind of a sneaky observation. It was originally empirical, and actually I think some recent STP theory tries to kind of justify some of this. And luckily, this is something that we can actually solve in a reasonable fashion. So let's say that I have my embedding, and I'm going to put it again in a matrix Y, just like we did before. Then in maximum variance unfolding, we compute the variance of our Y, which is, of course, maybe 1 over 2n, sum over ij, yi minus yj, where these are the columns of Y, like that. So this is a formula for variance. Okay, so what is this formula begging for us to do? Yeah. Expand the square. That's right. It's the only thing we know how to do in this class. Okay, so what do we get? This is 1 over 2n, the sum over ij. We get mod yi squared plus mod yj squared minus 2yi dot product yj. Like that. Okay. Notice that like this is the norm of yi, but it's summed over I and j. Similarly for the second one, right? So I can kind of combine these two terms and get rid of a factor of n here. And I can write it as follows. This is really the sum over I of the norm of yi squared minus 1 over n. Now here's kind of an interesting thing. Notice that I've got yi dot product yj, and it's double summed over I and j. So really the sum over I only affects the first term, and the sum over j only affects the second, right? So a different way to write this expression is the sum over I, yi, dot product of the sum over j, yj. Okay? Does everybody agree that this is sort of kosher? Okay, so we're going to make the same assumption that we keep making in our embedding algorithms, which is we might as well center about 0. Yeah? So in that case, we can assume that the sum of the yi's is equal to 0. Why would I do that? Makes things simpler. That's right. In particular, this whole thing is 0. Yeah? This is, by the way, just a useful fact. You know, like if you're doing variance, that like actually there's a simpler formula for it. Yeah. Okay. And this thing, if I take, remember that we define this matrix called the Gram matrix, which is the matrix of all dot products. So this is like the sum of all the dot products of the columns with themselves. So we can write this as the trace of G. Isn't that tidy? Okay, so let's look at the maximum variance unfolding. So we're maximizing the trace of G. So we're going to think of our variable as being the Gram matrix. Okay, so what is the Gram matrix? For one, it's positive definite, right? We know that because it's a matrix of dot products. Now, what is this second constraint saying? Like, what is this thing? You remember this from our previous lecture? What is the left-hand side of this expression? Yeah, this is the distance between point I and point j, right? This is just, I expanded the square, and then every time I had xi dot xi, I replaced it with gii and so on, right? And then this third constraint is a little bit tricky. So let's say that I had my data set, or my embedding, like y. Then remember we said y times 1 is equal to 0, like that. I can pre-multiply both sides by y transpose. In fact, I think we made this argument last time. And this thing is the Gram matrix, right? So in other words, if my points sum up to 0, then the Gram matrix times the vector of all ones is the vectors of all zeros. These are the same thing. Okay? So maximum variance unfolding, here's what you do. Rather than optimizing for y, we optimize for the Gram matrix G. Now, why is this kosher? Like I kind of forgot something, which is G came from a bunch of points. Well, because G is positive definite, right, I can factor it, right? I can always write like Cholesky factorization, LL transpose. So I can always extract an embedding from this thing. So it's equivalent, actually, to optimize just for the Gram matrix rather than to optimize for your embedding. But this is a convex problem. This is a set of positive definite matrices, semi-definite matrices, a convex set. And so finding the embedding that exactly satisfies your distance constraints and maximizes variance becomes a totally classic, what we call semi-definite program. So this is basically, there's software out there that just solves problems that look like this. On your homework, I believe you're going to implement it. The interesting empirical observation, so first of all, if your constraints here are consistent with a Euclidean embedding, then this thing will find one that satisfies your constraints. That's an easy thing to convince yourself. But there's two problems. One is, if the D naughts are not consistent with the Euclidean embedding, this thing, as we've written it here, can just fail, right? Because now the constraint is unsatisfiable. There's no Gram matrix that has the constraint here, right? So in practice, probably you would take this and you put it in the objective, right? You make like a wiggle room for it. The other thing is dimensionality, and this is where things are kind of interesting. Now, what you're going to do in your homework is you're going to extract the embedding by basically computing the eigenfactorization of G, right? Because that'll factor G as like, well, a big matrix of inner products, which is what you need, right? And the kind of empirical observation that you'll find, I hope, is that the number of non-zero eigenvalues for G is relatively small, which basically implies that like you have a low-dimensional embedding for your data, right? Those two things are the same. Actually, justifying that theoretically is quite difficult. And this is actually something that happens a lot in the sort of theory, practice, and magic of semi-definite programming. It's not so hard to write a lot of problems in this kind of form. And oftentimes, even if you have to relax some constraints, you get really nice solution to that problem. But proving that whole diagram should commute is actually quite difficult. So anyway, the sort of construction of this method is relatively straightforward. The analysis is really hard. But on your homework, you can just play with it, and you'll see it's really incredible that this thing works as well as it does. Okay, so we're mostly done for today. A few things just to mention, like if you like these kinds of problems, there are so many computational problems out there that range from theory to practice. For example, you could like look at a data set and ask like, do I have any business trying to embed it in a particular space? Can I find the right dimensionality, right? Like a parameter in a lot of the algorithms that we had here was that number p. You might ask, like, can I find that thing automatically? Like, what does that look like? You could ask for similarities, averages of metric spaces, and so on. All of these are tips of great icebergs. And it's worth noting that, like, solving a lot of these problems with an equal sign can actually be computationally intractable. So, for example, here, this paper considers some version of that stress majorization model that we talked about last time. See, there's like a d minus the distance from xi to xj, and they show that solving this problem to global optimality is NP hard. So in some sense, we have no business solving it, even though plenty of data scientists do in their day-to-day work. It's also worth noting that this area is adjacent to a very large and popular area in machine learning called metric learning, where you're given a big set of data points and some set of relationships between them, and you're trying to either parameterize those points or directly find a distance function that you can use to compare them, given these relationships. Like, these things should be close in my distance, these should be far away, right? And there's so much literature out there. There are many typical approaches. Some of them directly parameterize the unknown distance function. For example, here's a very reasonable one for a positive definite matrix A. This is called the Mahalanobis metric, which is just dot product with a thing inside of it. Or another thing you could do, which I think is the more popular neural network technique these days, would be take your data points, embed them into some other space, and then just measure similarity relationships there using the distances on these images. This is a technique called kernelization. It's very straightforward. But it's worth thinking about, like, there are many different loss functions you could use to solve this kind of metric learning problem. By the way, this survey, which is 2013, sort of right on the cusp of like deep learning stuff, like, but these folks were largely, I think, not cognizant of developments in that community. It was a really nice read. They go through all the different ways that you can kind of model this metric learning problem and translate, like if you have S and D are like sets of like positive and negative pairs, like I want to learn a distance metric where these points are close and these ones are far away. There are many different ways that you might measure that in your algorithm, and they lead to losses that are easier or hard to optimize and so on. So here are a few typical examples, like maybe you just say for any pair that's similar, the distance cannot be larger or smaller than u, larger than, oof. If I have a similar pair of points, I'm going to upper bound their distance by a number u. And if I have a distant pair of points, I will force their distance to be at least L. This is the sort of convex optimization strategy that gets used a lot. These days in machine learning, we probably use losses similar to the other two, which have some kind of a soft version of the same thing. A really famous example of this kind of metric learning technique, which of course is very widely adopted now that NLP is such a popular area, I think goes back to this word-to-vec idea, where you basically took the entire English dictionary and just embedded it in Euclidean space. The original paper did this using these sort of like, similarity was measured by like proximity in a sentence, that kind of thing. Of course, now NLP models use all kinds of fancy heuristics for improving this basic old model. Incidentally, a fun pointer towards some other modern research, just actually a couple days ago in our research group, we had somebody that came in and told us about fair metric learning, which I thought was a really interesting combination of this area and some outside stuff. So I thought I'd throw in a pointer to this work in our slides here. So the idea here is maybe I have a machine learning task, and I'm trying to like predict, I don't know, mortgage default or something like that, and I have protected groups or properties that I want to quotient out of my machine learning problem. Like I know that my model should not be sensitive to race or gender or something like that. Then you can imagine that like, well, the main ingredient that goes into a lot of these learning problems is the distance metric, right? Like that's sort of somehow what's underlying a lot of the loss functions that are happening here. Like anytime you see a minus sign in your learning problem, there's somehow a distance being computed. So it might make sense that even before trying to make your learning algorithm fair, you make the geometry that is being used to construct your learning algorithm fair. Namely, the way that you compare data points shouldn't be cognizant of certain properties or something like that. There are a lot of different notions of fairness out there, like individual and group fairness. And it's kind of an interesting modern problem to study metric learning, not just from the perspective of like positive and negative pairs, but also positive and negative attributes. Positive and negative is probably not the right term here, like protected. Where you want to make sure that you have an effective distance metric, but also one that's not using certain criteria. Yeah. Finally, I promise, one more additional direction that you might look into for embedding, which is very different from the algorithms we talked about, is a popular pair of algorithms. One is called TSNE, and the other one is called, oh shoot, I forgot the name of this thing. UMAP, I believe. These are like the bread and butter of data science community, and they're used to visualize data sets all the time. And if you think about data set visualization, it's a task that's very similar to what we've talked about, right? Like you have this big high-dimensional data set, you're trying to like put it in a PDF so it needs to be two-dimensional. You could apply any of the algorithms that we've talked about so far to that task, but oftentimes they don't work terribly well because data sets are very high-dimensional. And so algorithms like TSNE and UMAP, essentially what they do is maybe they prioritize small distances over large ones. And they say like, well, if I have to induce a lot of distortion in my data set, maybe what I really care about is local neighborhoods, and then I'm kind of fine with rearranging neighborhoods any way that I want. And so that's what's sort of reflected in these techniques. So for example, what TSNE does, incidentally, these are all extremely heuristic algorithms. I think they're basically accompanied with no analysis, which should scare you because they're used in a lot of very technical reports on data sets. It's kind of interesting. So TSNE computes a pairwise Gaussian between every pair of data points in your data set. Notice there's a parameter here, which is the variance of that Gaussian. And then it does a really funny thing, which is it embeds your data set. So it finds a new embedding y, just like we've done, but it uses, instead of a pairwise Gaussian, it compares a pairwise t distribution in the embedding to a Gaussian in the high-dimensional input. Now, I see a lot of furrowed eyebrows, and you should be, because that's a really weird thing to do. But the basic philosophy here is that the student t distribution, here's kind of a picture, is heavy-tailed, meaning that there's like kind of more mass on the outside. And so they view this as some means of like making their model a little bit more stretchy for large distances. So in other words, TS&E tends to like clump together points that are close to each other, and then at some point they grow distant enough apart, and it just doesn't care about them when it embeds. So here's like a very typical TS&E embedding. I think you've all seen images that look like this in data science reports, where like it tends to expose cluster structure really cleanly and data. One caveat, like this is a topic that I would love for you guys all to read about in your course reading thing, because unfortunately we can't squeeze it into today's lecture. This is the most popular algorithm in data science. Like this is how people visualize their data sets, but there are many parameters here. I mean, if you look at this algorithm, there's the variance of the Gaussian, then there's some parameters of the t distribution, there's the dimensionality of your embedding, and so on. Something that people figured out later, and they give these parameters cute names like perplexity, which I think is cute, is that these parameters have a really strong bearing on what comes out of this technique. So it's very easy to run TS&E in a way that will make you feel like there's cluster structure in a data set that doesn't have any. That just by virtue of like literally IID random drawing of points, some things are closer to each other than others, but then because of the way this particular model works, like if you're close, it wants you to be really close. So suddenly you start seeing clumps of points, and there are a lot of data science reports out there that people have since kind of discredited, where they like kind of point to the smoking gun of whatever cluster structure, and it's really not there in the original data set. It's just in the visualization. So this is one of these things that is a little dangerous. I've included a link in the slides to this fun applet that they have, where you can just like noodle around with the parameters to TSNE, and it interactively shows you like how your data points move around, and you will find it very scary. But I digress. And finally, there's another algorithm that people use more recently called UMAP, but it's essentially the same. It's very similar kind of structure. Yeah?
Is it like necessary for this clustering problem to have parameters that look like that, or would it be possible to have some algorithm that didn't?
Oh, it'd be fantastic to have a non-parametric clustering algorithm that is reliable. Yes?
So it is possible?
No. No, I mean, like, it could be, but there's certainly no consensus in the community as to what to do. Unfortunately, this is a big issue in data science. There's many of these embedding techniques, as we've seen today, all of which make qualitatively different results. It's very easy to choose the one that justifies the conclusion you want to draw about your data set, right? Because these tools are basically, their primary application is visualization, right? Like looking at data in 2 and 3D. And the reality is there's so many decisions that go into these models that really have nothing to do with the data itself, but can really bias how you analyze it. Yes?
Would you argue that this set of parameters is minimal in some sense, or?
Possibly, but I think we'd have to actually introduce the math here a little more to even talk about that. There are some areas where the answer is yes. So for example, what's a good example? In k-means clustering is sort of the simplest one. There's a famous research paper, I believe, by Tibshirani in like the 90s, where they talk about this elbow phenomenon, that you kind of look at the error from k-means, like the distance to your closest cluster center as a function of k. And they argue that like statistically this thing has this elbow in it, and that's sort of where you should choose k. But that's a rare occurrence. That doesn't happen often. All right, folks, so maybe we'll end on time for once. But essentially, this was our whirlwind introduction to this funny inverse problem of embedding a curved data set into a flat space. As we saw, there are many heuristics involved because it's a hard problem and it's not clear how to model it. Starting in our next lecture, we're going to dive back into the mathy side of this course, and we're going to introduce the Laplacian operator, which is going to be our favorite object to study for way too many lectures, basically for like a good solid 3 or 4 weeks. So with that, have a lovely Tuesday. Don't forget your homework, and I will see you on Thursday.